starting to experiment with this before I actually got to the full explanation. The series circuit, the most basic electrical circuit. So I've got a 12-volt supply. 1076. Yep. So I've got 12 volts, and I have two resistors. Here's resistance total, 10 volts plus 30 volts. This is what we should already be starting to grasp. So my resistance total is 40 volts. Thank you, 40 ohms. I'm trying to, I don't want to go too fast, but I'm trying not to go too slow. I'm speaking more thinking. Okay, the same current flows through each component equally. Only one path. Series circuit. So I've got the math in here. And we have this is our formulas up here. But voltage is current times resistance. Current is resistance divided by voltage. They're all up there. So I had a total of, if you remember back on the previous page, I had a 10 and a 30. They're in series, so they essentially act like a 40 ohm. So I can actually redraw it with one 40 ohm resistor, and nothing changes. It's the same circuit, same total resistance, same current. Right? And then we've got the formulas, and I can get into that, but it's essentially we've already been doing it with our formulas earlier. Yeah, this is just going over the formulas. Voltage drops and further application of Ohm's law. This refers to the loss in electrical pressure, or EMF, caused by forcing electrons through a resistor. Because there are two resistors in the example, there will be separate voltage drops. Each drop is associated with each individual resistor. So again, we've got a battery. We have three resistors. Yeah, see, this is actually, they made a typo. The description of this has two resistors, but there's three. There's a 1, a 3, and a 5. So our resistance total is 9.
Now, it's now the resistance, like the force that goes through it, the pressure,
that's volts,
is proportional to the size of the resistor, or the like
volts,
a lot of resistors were the same size, but they have different resistance values.
Our supply voltage will be the same. It's a 12 volt or 24 volt system. The current will change based on the resistors I have. Now, I'm getting to what you're asking.
Right.
The voltage drop will, if I change this resistor to a different resistor, these voltage drops are going to change. And the resistance will be the same. If I change any one of these resistors, either high or low, the current will change. The current will change. The voltage stays the same. If I change resistance, the current will change.
Okay, got it. All right, I was thinking the size of it as one resistor, but the size of resistance in total.
You can think of it as one resistor.
Right.
But if I change one resistor, that one resistor that I create out of those now has changed. So if I have a current voltage and I change the resistance, the current is going to change. If the current changes, the voltage is going to change on all those. And that's to be expected, because if I have 12 volts here and this is 3 volts, if I change this to a different resistor, this is no longer going to be 3 volts. And since they all add up to 12 volts, if this voltage changes, these are going to change as well. So ultimately what's happening is if I make any changes, the resistance total will change. And if that happens, the current will change. And then if the current changes, that affects the voltage drops for each of the resistors.
But the current, even though the current changes, it's still same throughout the whole
The
thing.
only thing
right?
that, yes, you are correct. The only thing that won't change is my power supply. That's my battery. Nothing's going to change that.
Okay.
But you're right. It is a series circuit. The current, whatever the current is that changes, will be now the same current for each of those individual resistors. We did this. This is the same thing. They're taking resistor 1 3, and 5, adding them together to get a total current, and then using the formula to figure out what that current is. They're showing the voltage drop 1, 3, and 5. I don't want to spend any more time on this because this is our chart. Voltage sources in series. A voltage source, we did some of this last night. A voltage source and is an energy source that provides a constant voltage to a load. 2 or more of these sources in series will equal the algebraic sum of the sources connected in series. The polarity of the sources must be considered when adding up the sources. So here they're showing negative. All the negatives are on the left side. So we have flow clockwise, and we would have 4.5 volts. So they're giving us the formula. Voltage is E, voltage total equals 1.5 plus 1.5 plus 1.5, and our voltage total, which would be ET, is 4.5. Yes?
In this class, is there a difference between additive and algebraically?
I don't think so.
No, it's the same. Cool.
Yeah. Additive is algebraic, but algebraic isn't necessarily additive. Additive could be,
This is adding a bit, right?
algebraic could be, yeah. I guess the formula is the best way to look at it.
Right.
No, I don't. I mean, I'm trying to decide whether I go any further in explanation on it, because in this material there are typos and there are different terms used. So the same person didn't write all these chapters. And you will find when you get in the field, just like anything you work in, there's a lot of times more than one word for the same thing. So here we have the exact same thing, but they've turned the battery around. And if you were working in the lab last night, you noticed that if you once you turn one battery around, it's going to cancel out the same amount. It'll cancel out another battery, or basically from your 4.5 volts, you're now going to have 1.5 volts.
Is there any, other than experimenting, is there any purpose?
No practical purpose, no. I can only imagine that this backwards battery would start to heat up and expand and degrade. Because now you're forcing electrons to go the opposite direction. But they were trying to give you, this is one of those to think about. I don't know any practical purpose. Kirchhoff's law. A law of basic importance. The sum of all the voltage drops equals the total source voltage. You want to remember that. So we have 24 volts. They don't give us, oh yeah, there it is, 10 volts and 14 volts. If we added another resistor in here, these would drop. And all three would add up to 24.
Is it still equal to
Still Kirchhoff's law. He made the law, it's going to stick. Okay, so you will do a little bit of this, I think, on the test in a week. You'll figure out what your total voltage is, and you'll learn your other 2 voltages. So the difference is whatever the difference is from your total. So you take 24 volts and you subtract the 22 volts, and you get 2 volts.
The S is, what does that stand for?
24 volt. ES is, and this is an example of what we were just talking about. Usually you'll see volts total. This is volts source. It's the same thing. You just have two different people create a diagram. So ES is your source, your battery.
And so
ET would be your total voltage, which is your battery.
like E1, E2, and E3, they're asking for the voltage drop.
They're at what the purpose of this was to figure out this voltage drop, knowing the other 2. So 12 and 10 or 22, and then you're missing the remaining 2 to get to 24. So that's a 2 volt drop. and that was it. Is that the same one? Or is this one different? Determine the value of, this is different, voltage. They didn't put the R, and you don't have to. They're asking for volts, and when they put a little number like that, they refer to resistor. So they're asking for the voltage for R4. For this example, the current is 200 milliamps. First, the voltage drop across each of the individual resistors is determined. You can do that because it's a 200 milliamp current. It's a series circuit. So the current is going to be the same for all of them. So with current and resistance, you'll get the voltages. You don't have resistance here, but you've got resistance for the others, and you've got current for all of them. Once you know the current and the resistance for these other three, and you know your total voltage, you're just figuring the difference. It's just like the problem we did before, but we have 4 resistors. And then that talks about voltage dividers. I don't know. This is a 200 volt source. I can see that because they're showing me right here before they've even hit your first. So we've got 150 and 90. What am I missing? 10. Oh no. Okay, they are. Oh, they're going through a load. This is not Kirchhoff's law. This is something different.
Voltage dividers.
Okay. We're not. That's okay. This is going to have its own voltage drop, but we're not going to tap downstream of it because that would be we'd get 0. So if we come straight off the power supply, our ground, we tap a ground off. Here's our load. So each of the loads are connected to the ground of the battery, and then each of the loads come into different parts of the resistor. So this one doesn't have a resistor between it. Goes straight to the battery. So 200 volts is picked up here, and it's not dropped. We go through this first resistor, and we're losing 50 volts. And in here, we're losing 60 volts. But this one here is getting 50 volts because we lost 50 there. So it's Kirchhoff's law. We've got a voltage drop across each of these. We can tap off for different voltages along the way.
So the number 2 gets just the drop in voltage?
Yeah, when we get to number 2, this R3 has a 50 volt drop.
Okay.
Because I'm seeing 200 here and I'm seeing 150 here.
Right.
And then when I get to here, I've got a 60 volt drop here.
So the number 2 would get how much?
So number 2 is going to get 150 volts.
So we'll get okay.
So if I come straight through with no resistance,
You got
I get 200 volts. I'm losing 50 volts, and I tap off downstream of it, and I can take a load for 50 volts here. And then there's another voltage drop and another voltage drop.
Now, in the example, what you're showing in the book is the voltage across each resistor, the voltage dividers. 90 for R1,
Yeah, if you
and then
tap.
you go 60 for R2 and 50 for R3. So I don't know where they come up with those other.
Okay, so
R2
this one,
is-
this is losing 50. This is losing 60. This one we're not tapping off of downstream because it would be 0. Because we're right up against the. So I can tell you the voltage drop. What's that? 40. It's 40. 200 minus the 50 minus 60. So you've got 40 left over. So your voltage drop here is 40. But if you tap off downstream of it, you're at Kirchhoff's law. You're at 0. There's nothing left.
Sorry, you and I are trying to figure this out more. So from the voltage source, is it traveling up and then to the right?
So it's going this way.
Okay.
This is they're showing current total, but if you completely ignore everything in the middle, here's my ground. They all see a ground. This load is connected to the other side of the battery with no resistors behind.
Okay. So those are all grounded down there in the bottom, and then the flow is only going up and then to the right.
So simulating, as we've drawn other drawings, here's our current flow right here.
Okay, so yeah.
And then
The
we
other
have
way
voltage
to-
drops along the way. And then we're tapping off between these voltage drops.
Why do the two arrows look like it's pointing the opposite way then? Not those arrows, to the left, see on the top and bottom?
Yeah, they look
The
like
voltage-
they're
the
pointing
voltage-
up.
And then the
No,
voltage
the
total.
IT voltage.
IT.
Left side, left side.
More left,
Left.
a little more.
Right there.
Yeah, there's two. Those other
You know,
That's
they may be drawing it this way.
So if it's that way, then so how would that work?
Okay, well, what it is since this outer loop doesn't have any resistors, this would be 200 volts. If the voltage is moving this way, then my voltage drop, I think,
Well, if it came into I2 from the bottom, it would come up and see the 50 volt drop between R3.
see the 40 volt.
So all the way to the right,
Yeah, to see the 40
and
volt.
it would go up, it would lose 50 volts through R3 only. If it comes up through IT,
yes.
It's not being used.
Now, no, and to keep it simple, if you remember, it doesn't matter which way the electrons flow. The circuit doesn't change. So going this route, the way I was explaining it is the easiest for me to visualize for you, but it's going to work the exact same way. So the voltage drop here is the same. The current through here is the same, but this is reading difference. So literally, the voltage drop between here and here is 50 volts. So from this ground to this, the one with no resistance, it's 200 volts, but I still have a 50 volt drop.
The
So
ground is
these
still-
still have their, I think what they're showing that this is the ground on the top. Because they're showing arrows pointing up here. So they're showing, and I'm used to all these drawings, and I think you're the first person to notice it's the other way.
Sorry.
But all these drawings are going this way. No, this is helpful because we all learn, and I'm learning this too. So I'm realizing that with your question that the flow is the other direction, but it doesn't matter. It doesn't change anything. My voltage drops are still the same. So since I'm going from ground to 200, no matter which way I'm going, I still have a 50 volt drop in this line.
You said on that, you said 50, 60, and then 40.
I could write these. Yeah, I could write 50, 60, and 40 here.
The 60 minus the. How'd you get the 40?
We pulled, it was 50, and then 60, and 50 and 60 to get to 200 was 40 remaining. These 3 will add up to 200. They've given us that the difference between these two lines is 50. So my voltage drop here is 50 volts, no matter which way I'm going.
I understand 50 and 60, I still don't understand 40.
Well, the 40 is, Kirchhoff's law says that each of these 3 resistors have to add up to 200 volts.
That's over.
That's over 240.
But is the
No,
voltage-
that's the
Yeah,
voltage
this
left
is the
over
voltage-
after the resistors get applied to the voltage.
Yeah, I've got a 50 volt voltage drop. So I'm pulling. So now this 200 is dragged down to 150 at this point. And then when I drag this 150 down another 60 volts by this one.
Okay, so you got 100. That should be 90 then?
Well, what I have here is I've got 50 plus 60 is 110. So that's 90.
Okay, yeah.
Okay.
So it's not 40 anywhere. Yeah.
Yeah.
Okay.
My mistake.
it's public math.
Yeah. Public school math.
That's all it is.
Yeah, I apologize. Hopefully you will remember the concept and not the values.
Yeah, the only 40 I saw was 200 minus 150 minus 90 is negative 40. Yeah.
But you make a valid point. It's for me it's easy to visualize this way, and I've been looking at these diagrams this way.
Is that fall in line with the difference in philosophy between conventional flow
Yes.
and electron
Absolutely.
flow?
Dead on.
Okay.
Yes.
So there's 2 different ways of looking at it. It's both, but they both work.
Because because, and if you remember conventional flow versus,
Conventional is from
conventional is the way we've always thought it,
yeah,
positive.
from positive to negative, and
And
electron is
then,
negative to positive.
the
Abundance of
electron-
the negative charges go to positive
The
side.
electrons are trying to get to the spot that doesn't have any electrons.
Yeah, the lower side.
Yeah.
So your point,
electron
so
movement.
I think it explains this way for me visually easier, but it's identical in the opposite direction. We are at 7:30. We'll take a break here shortly. What time do I have you?
8:50.
Oh, I've got 20 more minutes?
Yes.
I'm going to use it. I'll get you a break between. Okay, this actually, the 11, that's the end of that one. One more, let me see how long it is. Did you bring a coffee pot to this class?
It's just the way
Yeah, we really.
the two theories, conventional flow was basic measurement. Yeah, but it really wasn't. But most books are written.
Okay, this one's only 3 pages.
That's flow. Kinda.
No, wrong,
That's what
not the mistake.
no matter which way you go, you're gonna get the same result. Just have
It was a page.
makes it look easy. The way he was talking.
Yeah.
We have the rest of the evening left. I'm happy to sit down and draw and answer questions, and we will work at our own pace. We can do whatever we want. So, we're catching up to parallel circuits. 2 or more electrical resistances are loads connected across the same voltage source. And the same voltage source is why the voltage is the same in a parallel circuit. They're connected across the same voltage. It's called a parallel circuit. The primary difference between the series and the parallel is that there's more than one path. Each of these parallel paths is called a branch. The minimum requirements for a parallel are a power source, conductors, which are our wires, a resistance or load for each path. 2 or more paths.
A load for each path?
Each path has to have a load. And when I draw the river, I haven't been taking that into account because if I don't put a load in there, then it was like we were talking about earlier, where I put a jumper across that variable resistor, the power is going to take the path of least resistance. So if one of these paths does not have a load on it, that's the path of least resistances, and the others are just going to drop. They're going to lose their current. This they drew. This to me is a little confusing from the way most of the other drawings are. This is probably drawn by yet another individual. But all you can do, you can just draw these straight down. Or you can bring them together and down. Doesn't matter. They still make the same point. So that is 2 resistors in parallel.
So can you make that down into a singular circuit if you wanted to?
What I can redraw it like this. That's the same thing. Or since they're parallel, I can use the x over 1 and combine the 2 resistors. The combined resistors, remember, will be lower than the lowest of any of them. And then I can actually treat it like one resistor. And we will have to do that. In a lot of these problems we're going to do later, schematics, you will have to do that. Because you're going to have resistors downstream and upstream, and in order to get the current for that circuit, you have to treat this as one resistance. So you'll have to combine them to get one resistor value for those 2. Then you can add them like you do in a series. Once you can add all the resistances, you get your resistance total, you have your voltage, now you know your current. Now you go back to this and you go, okay, my current up here is whatever I figured out, and down here is whatever I figured out. But it splits here. And we'll talk later how we divvy this up and determine which is which.
When you're doing 2 resistors and you're trying to find the total,
These are parallel. So what I will do, I combine them.
Can you do the R1, R2?
It's, you have, yes, it's the x over 1 plus x over 1. Or that inverting, like I started doing. It's not on the board anymore. You cannot add those. You cannot average them.
So it's in here, so it's the R1 times R2 over R1 plus R2.
Yes.
You could just do that with 2 only, right?
No, you can do it for 3, or 4, or 20. You just keep, I mean, on your, if you have a scientific calculator, you should have an x over 1. So you just do, you could just go x over 1 plus x over 1 plus x over 1 plus x over 1, and then go
Convert the total.
and then hit enter, and then you'll get a decimal, you hit x over 1, and then you'll get a whole resistance on this value. We'll do it. We're going to do this. We haven't really got into this much. I'm just kind of getting your feet wet. But the point I wanted to show you here is eventually we're going to take those two and do that math and treat it as though it were one resistor. Because in order to get the total resistance, we have to get it in a series circuit. It won't physically be in a series circuit, but we can treat it mathematically as though it were. Okay, and so total parallel resistance, the voltage across any branch is equal to the voltage across all the other branches. So we saw here, whatever this voltage is attached to both ends of those resistors. If that's 24 volts, we each see 24 volts. The parallel circuit consists of 2 or more resistors connected in such a way to allow current flow to pass through all of the resistors at once. That's my river of many paths. This eliminates the need for current to pass one resistor before passing through the next. When resistors are connected in parallel, the total resistance of the circuit decreases. The total resistance of the parallel combination is always less than the value of the smallest resistor in the circuit. And that's the example I use in the turnstile. If it takes 5 minutes to get through each one of these, if we're going through one for this whole class, it takes us 5 minutes to get through one of them. If I open up another one, if they're the same resistance, if it's 5 minutes and 5 minutes, we just cut it the time in half. So if this is 5 ohms and 5 ohms, in this instance it would be 2.5 ohms. If this is 5 ohms and 10 ohms, or think of it 5 minutes, 10 minutes, the fastest we can get through here, if we have to pick one, the whole class will get through in 5 minutes. The other one would take us 10 minutes, but if we have them both, suppose we're just going through the 5 minute alone, we open another path, now it's less than 5 minutes. That makes sense. Are you doing 5 and 10? So 3 and 3.3333. And 3.3 minutes to get through a 5 and a 10 mean when we both start at the same, we all start at the same time and we all exit at the same time. Meaning, you know, as fast as you can, we're all bunching up, going through whatever one's available when we cycle out. Yes?
So I understand what you're saying with that example of people going through that, but I just don't understand. I'm reading through the book and it's saying the more resistors that are added, the lower the resistance of the circuit.
Yeah. So if we're at the grocery store and we're all there buying groceries, if we open more,
There's not as much amperage when we open one spot, it goes through another spot.
Yep.
That's why.
So the whole class, we're buying groceries and there's one register. You got a whole lot of slowing down.
That's all the current.
Current.
Which amperage are in.
Current is volume. The number of people going out to their car is going to be less. Now you bring open all the registers, and we can go through all the registers. Now you're going to see more people flowing in the parking lot faster.
So can you manipulate that if you put in high resistance?
Yes, you can do both.
Slow
You
it
can
down.
change the resistance, and you can change the number of resistors.
If you tighten the turnstiles and make them harder to turn,
I can
then
slow. I mean, if I tighten this and make this turnstile, if this one's rusty, it takes 10 minutes for everybody to get through, and this one's working just oiled, and it takes us.
Right, that was 100,000, that was 10,000,
Yeah.
that was 50,000.
So we can change them. They can be changed. But if this one's friggin' rusty, and then I could always add it, open up another one, and that's going to reduce the resistance too.
And the reason why you would have that is to have something that requires the same voltage out of all the resistors, but you want a different amperage going to them.
Which you're going to find. I almost have to get into what a circuit board is and all the things that are happening, because as we build resistors into a circuit board, this voltage is not taking pretty much ending up at one place. It's going through, it's spreading. These are not necessarily resistors. This could be your aircraft with one big battery, and you're running lights, and you've got a toilet.
Right, yeah.
I mean, you've just got, there's all these pathways. So the resistors, we're not so much adding resistors, we're adding loads. So when we have that aircraft battery and all these other systems, they all act as though resistors. They do have an internal resistance. We have all these pathways. So when we're manipulating resistors, really you can think of this as a bathroom light and a coffee maker and all the various systems.
Because certain things require a different amount of
Yeah,
current, even though they'll still work with the
they
same
have a
voltage.
certain amount of draw. They need current.
Like a hairdryer.
Yeah.
You're gonna need more.
And really, see, the vehicle, the aircraft has a battery. Our house has 120 volts. The house has 120 volts. So if we want, the refrigerator is going to have less internal resistance because it needs more current. So that motor, when I try to do resistance to it, it's going to be less because it's designed to let a lot of current in. It's going to be, it needs flow to move. A little tiny light bulb, my night light, is going to be higher resistance because it doesn't demand the flow.
Yeah, I mean, that's my question.
So we're looking at just, there's so many different things that all these pathways aren't necessarily going to the same place. Cool. If you notice, there's a stairway in here. So we all have to get that one stairway. So that would end up with another resistor here. Here's the stairway.
I have to be upstairs.
There's an escalator on the other side.
And here's my
Also an
river
escalator.
source. So the pink ones are your total current, and the yellow ones are your pathways. And the three pathways add up to all the pinks are the same.
How come you never use like the freeway as an example?
Because I boat, I water ski,
Oh, okay.
and that's all I'm thinking about.
And I think of cars as electrons passing by.
See, I think you could do the freeway, but now I'm thinking mass and atoms, so I think the closest thing would be water flow. In fact, when you go through all type of electronic class reference water flow, this is the most closely related. You start closing a valve on a sink, and that's your resistor. You don't quite have that on the freeway.
I don't mean to backpedal, but I am just a little
Too
bit
late.
on the voltage divider. I understand that divides the voltage, but I don't understand how it divides the voltage.
Okay, you remember that I have voltage drops.
No.
And I don't doubt that you're not the only person. We talked I have a 24 volt power supply. These don't have to be resistors, but then the voltage drop, I guess it would be. So I should have added 4. I'm going to add 4 resistors just to keep it the math. So that's 6. Each one of these is going to have a 6 volt drop. Yes. So, I have a 24 volt volts total, and then each resistor has a 6 volt drop. It doesn't matter the resistance of these because I could put 5 ohms in there. I could put 25,000 ohms in there. If there's 4 of them, if they're equal anyways, or whether they're equal or not, all 4 of them are going to add up to 24 volts. It's just Kirchhoff's law. So when I pass this first resistor, I lose 6 volts. So if I measure from my ground to here and here with my meter, this is my red lead. I measure here, and my ground is here. I'm reading 24 volts. If I literally go to the other side of that next volt, next one, I'm going to have 18 volts. Is that right?
Yep. Yeah.
18 volts. and then I move to the next one.
Well,
So right here I'd have, if I wanted to, if I literally measure 18 volts from here to here, and then I lose 6 more volts, so I've got 12 volts. So if I'm running, if this down here happened to be a big old hydraulic pump, and maybe this thing's 24 volts, and this is my voltage drop is 20 volts.
Right.
This thing's using 20 volts because it's bigger. My other loads might be, I've got 4, so I might have 2 and 1 and 1 volt. This might be a fan for that motor. This might be a light telling me that it's operating. But I can, if I go anywhere in between here, I'm going to get different voltages.
But the voltage divider, that's what I was confused about, is how that works. Like,
It would be
You're
that
just-
circuit. It would be literally this operating circuit, and I physically connect a positive wire here, and I use the same ground. So right in here, I can take this wire and bring it over to and share the ground. This is my ground, and I could run something else right here that would be, if I lose 2 volts here, this would be 20 volts.
oh, so it's two different sources.
It's one source, but after I lose
Oh,
voltage,
okay, I gotcha.
when I have a voltage drop, the voltage changes. It's like going downstairs. They start to drop the further I go. And I can tap into whichever one I want.
I gotcha. So you're really just dividing it by 2 different.
I'm taking the 24 volts and I lose 2 volts, I lose 1 volt, I lose 1 volt, I lose the other 20. If I need 20 volts, I'm going to tap in right here. If I need 19 volts, I'm going to tap in here. I can get 19 volts right there, even though my source is 24 volts.
I gotcha. That makes sense.
We're looking at thermistors over here. That's not related to that.
That's fine.
What's the difference between a negative temperature coefficient and a positive temperature coefficient?
I think what they're asking is, I can have a thermistor that will react cool or hot. I can turn on a heater. I can put a thermistor that detects something maybe too cold and give me a higher resistance and a circuit that will turn on a heater. Or I could have something that's detecting heat, negative and degree, so it's looking for heat, and then I would turn on a fan.
So the difference between the increase of heat versus the decrease of heat?
It's not, what it is the material they use. The material they use is conductive, and it has a resistivity, and that resistivity changes based on temperature. Which, depending on the material, I can have that resistivity, the continuity or the resistance drop if the material gets cooler.
Okay.
Or I can have the resistance drop if the material gets hotter by using a different material.
So will they identify it as a positive temperature coefficient, or they just say temperature coefficient?
Well, if you had a thermistor, it would tell you the temperature that it reacts at. So it might say minus 40 Fahrenheit. And it could be an open circuit, it could be a closed circuit. You may want to turn something on, or you might want to turn something off at minus 40 Fahrenheit.
Well, I'm thinking more right now that the terminology we come across, will it say a positive temperature coefficient, or will it just say temperature coefficient? This is something coming across the book.
You know, I'll have to get back to you on it. I'll make a note. But normally when you get a thermistor, it'll just give you a reactive value, like a resistance. It'll say what temperature you get open. So a thermistor may have 3 connections on it. It may open, once it activates, it may open this circuit and close this one. So you could use it either.
So if it got too hot, it would turn off the heater, something like that?
You could, I mean, if you just put it in, if it switches, it just switches it at 0, say 0 Fahrenheit, you could connect it to these two and have something turn on. Or you could have something
So
that's
if I need
always,
like more voltage and I
this
don't
could
have
be
enough
always,
voltage,
this could
just
be
draws from another cable.
closed above
She's saying that
0 Fahrenheit, and this would be open, and they could swap.
your
once it
resistors
changes.
are
So
always
you
going
could-
to add
you could
up
have something
to
on either
Right.
one.
your source,
Turn
right?
something
Right.
off
And then
another
that
off,
one
or
needs
just use
20
the two
volts
or
to
these
work.
two or those
Right.
two.
So then
Depends on
going
what you
through a
want.
certain
It's
amount
like the
of
inside your house.
resistors is going to add up to 20.
But if you can't get to 20, right, then you get.
Okay, I have 1 minute.
He did it
There's
like
3 resistors in parallel.
he did it like he did it.
This is just another parallel circuit. We're gonna be doing a bunch of these next
I don't
month.
know why I'm so.
I appreciate your patience, and I know I'm grinding you. I'm hopefully what I'm covering is adding to what I'm already covering. It's building on. So why don't you guys? We're in lab time, so you can head out. You guys can take a break. This is work at your own pace. So we can do problems. I have sample problems.